Hello everyone, welcome to what will be pre-lecture 12. Just reviewing some stuff that we've already covered in class and then going through how we solve problems related to acid-base equilibria for a weak acid. So just picking up where we left off in class, just a reminder to be memorizing your strong acids and strong bases. And of course, the difference between a strong acid and a weak acid, or a strong base and a weak base, is that strong acids and bases totally ionize, meaning that they fully dissociate. Whereas a weak acid or weak base is only going to partially ionize in water. And so we can, of course, describe that with an equilibria, like something shown here at the bottom of the slide. Okay, so just a reminder about that, as it is very important to the rest of this unit. With that, when we do have a weak acid or a weak base, we can calculate basically concentrations of reactants or products, or both, or equilibrium values, Ka and Kb, using these equilibrium expressions, right? And so as Ka or Kb gets bigger, that means that the respective strength of our acid or our base is going to go up, right? And so as Ka or Kb gets bigger and bigger, the strength of our acid or our base increases, okay? So I have one more definition for you of what makes an acid and what makes a base, and this is called the Arrhenius definition. And so it is in some ways the simplest and most restrictive of our definitions, and it says that an Arrhenius acid is something that will dissociate to form H+ ions, while an Arrhenius base is something that will dissociate to form hydroxide, ROH-. And so this is certainly going to be true for something that is a strong acid or a strong base, but for a number of weak acids and weak bases, this won't actually be true. And of course, that is why we have our other definitions, such as our Bronsted-Lowry, which is defined in terms of the transfer of protons, which is H+, right? So a Bronsted-Lowry acid is going to donate a proton, whereas a Bronsted-Lowry base is going to accept a proton. And then, of course, we have our Lewis acids and bases, and that is our most expansive definition, where anything that is a Lewis acid will also be a Bronsted-Lowry acid, will also be an Arrhenius acid, and anything that is a Lewis base will also be a Bronsted-Lowry base and can also be an Arrhenius base. Okay, so that is our most expansive definition, and basically is the good news is that anything that is an acid in one of these can be an acid in any of them, right? And so as we go from Lewis acid to Bronsted-Lowry acid to Arrhenius acid, those definitions get more and more restrictive, but hopefully you can keep them straight and identify what is what, okay? So those talk about how we solve equilibrium problems related to acids and bases. And so with that, let's say we're looking at problem 15 on our in-class worksheet for week 4 and 5 here. And I ask you to calculate the pH of, let me make sure I get my marker up here. Calculate the pH of a 0.05 molar solution of HCN. And I give you a Ka value for that. I also ask you to determine the percent ionization of this solution. And so a couple things I want to point out here before I do anything else. Hopefully, if we look at the chemical identity here, HCN, we realize this is not one of our strong acids or strong bases. And so we know it's going to be a weak acid or a weak base. And we are given information about the Ka. And if we're given information about the Ka, that means that this must be acting as an acid, right? So we know that this is going to be an acid, and so when in doubt, in an equilibrium problem of how to start, I always recommend writing out the relevant chemical equation as well as the equilibrium expression. And so if we think about HCN acting as an acid with water, it will, in a solution, interact with water as a pure liquid. and that will be in equilibrium. So if HCN is our acid, it is going to donate a proton to water, and so that will give us H3O+, which is a molecule we call hydronium, right? And it will also give us our conjugate base, which is Cn-. Within this, we can, of course, then write our Ka expression, and that is going to be equal to our products over our reactants raised to their powers, as per always, right? We're pros at that already. And so we have H3O+ and Cn- as our products, and then our only reactant we need to include is HCN, because water is a pure liquid, right? And so if we're asked to calculate the pH, what we're really asked to find is our concentration of hydronium right here, right? So we want to figure out what our concentration of this at equilibrium is going to be. And hopefully those words are ringing a bell to where we should be building an ice chart here. And we are given an initial concentration of our reactant, which is this 0.050 molar HCN. Water is pure liquid, so we can go ahead and cross that out. And then if we think of if we're not given any information about H3O+ or Cn-, we can assume that their concentration is 0 under initial conditions. Because of that, we know that our reaction is going to move from reactants towards products, so that means it's going to be a minus on our reactant side and a plus on our product side. And our coefficient for everything in this chemical reaction, it's very nice that it's 1. So this is just going to be minus x on our reactant side, plus x on our product side, and our equilibrium term, if we just combine those first two rows, ends up being 0.05 minus x, x, and x. Then, if we want to solve for these values, we plug in our Ka as well as the information that is found in our equilibrium row into our Ka expression. And so our Ka is 4.9 times 10 to the minus 10th. That is going to be equal to x times x, which we could also call x squared, over 0.050 minus x. And if we look at this, we are just so lucky that our Ka value is times 10 to the negative 10th, which means we can use our x is small approximation. And so instead of needing to use the quadratic formula, we can just cross out that x that is in our denominator and then solve for x from there. And so when I do that, I got a value for x equal to 8.89 times 10 to the negative third. And I know that that is going to be basically both of these values here, which are in concentration. So I'm just going to go ahead and give it the units of molarity. So we've found x, which is great, but what does the question actually ask us for? It asks us for pH. So hopefully you remember that pH is going to be equal to the negative log of the concentration of hydronium, H3O+. And so if we take the negative log of x, which is equal to our concentration of hydronium at equilibrium, I got a pH value of 2.05, which if we do a quick logic check, we know any pH value less than 7 is going to be acidic. If we have something that is an acid, it of course makes sense that our pH value would be less than 7. And so a pH value of 2.05 makes a good amount of sense. Then finally, I ask you to also determine the percent ionization here. And so the formula for that is we just need to take x and put it over our initial concentration. And so when we do that, x, of course, is 8.89 times 10 to the negative third. And that is going to be over our initial concentration of 0.050. Because this is a percentage, that means we need to multiply it by 100. And when we do that, I got a total value of 3.6% ionized. and that will be our percent ionization, which again, if we do a logic check, makes some amount of sense. We know this is a weak acid. We know our Ka value is quite small, and so it makes sense that our reaction is not going to be very ionized. In fact, only 3.6% worth. Okay, so that is how you solve an equilibrium problem with acids and bases. That will be it for this pre-lecture video. Hope it was useful, and if you do have any questions, of course, please feel free to let me know. Otherwise, I hope you have a great day, and I will see you in class.